Hi, my name is Axel Plinge. I'm going to explain deep compression in a nutshell. Deep learning sometimes produces huge models, and deep compression provides automated ways of shrinking them down again. The problem is that deep neural networks, or DNNs, are typically trained on clusters of graphical processing units. As such, they need considerable resource at runtime or inference. Deep compression can automatically reduce the model complexity. This allows the compressed models to run with consuming less energy and on embedded devices. One example of deep compression is the reduction of a natural language model. Researchers reduced it to 4% of the original size by a combination of quantization and hashing. This got a popular speech assistant from needing the cloud to run on the phone independently. Another example is the reduction of AlexNet to SqueezeNet or MobileNet. AlexNet was a very successful but bulky image classification and detection convolutional neural network. Through some clever structural changes, researchers achieved a reduction to about 2% of the original size with similar performance. Deep compression techniques can be roughly categorized as 4 modules that can be combined in sequence. First, pruning techniques. Second, subspace or low-rank approximation methods. Third, we have quantization. And finally, lossless coding. The first technique is pruning. Pruning can be implemented as pruning individual weights for sparsification, or removing neurons or whole filters, which gives a direct speedup. This removal can be based on, for example, value, validation loss, or even explainable AI methods. Retraining is required to keep a high performance of the network. It can be seen that iterative retraining leads to the best results. This means that each time part of the network is removed, one or more epochs are trained, which is computationally expensive. Another family of methods I will count as pruning techniques directly modifies the convolutional structure of CNNs. One method is flattened convolution, where the high-dimensional convolution is replaced by a sequence of one-dimensional convolutions. This obviously requires retraining. The number of parameters is greatly reduced and the speedup of a factor of 2 is reported. Another clever idea is the depthwise convolution, that reduces the required number of multiplications by rearranging them. This obviously requires also retraining. We have a speedup of a factor of 8 reported, and also the number of parameters is greatly reduced. Next technique is subspace or low-rank approximation methods. Singular value decomposition allows to express a tensor with lower rank than size as a product of smaller matrices, as shown here. This also means that we can represent it as a product of 2 smaller matrices, and thus 2 small array tensors. This is done post-training and leads to a direct reduction of size. The next technique or family of methods is quantization. Uniform quantization uses less bits per weight and eventual activation. For example, 8-bit integers instead of 32-bit floats. Retraining can improve the performance of the network. When going down to very few bits, retraining is needed to keep the performance. The extreme is using 1 bit only. Those binary networks provide big speedups as they remove the need for multiplications. Adaptive quantization takes into account the distribution of the weight values shown here. It is implemented as vector quantization or clustering of weights. It is done post-training, and for the inference, it can be implemented as simple lookup table. Last technique is coding. One applies Huffman or entropy coding to the individual values. This is a lossless compression step. The output representation is non-uniform, meaning that values are mapped to a variable number of bits. It is done post-training and works directly on the quantized representation of the network. To summarize, Decompression is automated reduction of model complexity for inference using less energy and on embedded devices. Techniques are subsequently first pruning, which is removing weights, removing filters, or removing dimensions. This leads to compression and direct speedup and requires retraining. Second, subspace representations. These can be done by singular value decomposition and restructuring. This leads to a compression and a direct speedup and has to be done post-training. Third is quantization. It can be either uniform quantization or adaptive quantization, which is clustering of weights. This leads to compression. Retraining is done in the uniform case. The adaptive one is done post-training. Last, coding can be applied. This can be, for example, Huffman or entropy coding. It leads to compression and has to be done post-quantization. I hope you found this presentation useful. Thanks for watching and goodbye.